thank you all for joining us today. It's great to see so many people here at the Google office, and thank you to Google. I'm going to talk about explainable AI. It's a lightning talk, so I'm going to whiz through it, a very high-level view. Okay, so I'm going to talk a little bit about explainable AI and the work we're doing at Seldon related to machine learning deployment. Seldon's focus is on enabling organizations to move their machine learning models out of R&D and into production. So next slide. So our purpose is to help people shape the future by bringing machine learning deployment to life. So how do we do that? Well, the first problem is that most models that are created do not actually find their way into production. And most organizations are in this kind of initial phase, which you can't read all of these points on here, but effectively this is a cycle of understanding your business problem and then going about gathering data and building and training models. The big challenge is in operationalizing models. So this cycle that requires a large amount of supporting infrastructure to actually serve and manage machine learning models in production. So the problem here is that it's not just in most machine learning projects, the machine learning code only represents one very small part. This paper actually originated from Google, where it's describing the technical debt associated with this supporting infrastructure. So a huge amount of cost to build and maintain machine learning infrastructure, and Seldon really focuses on providing the infrastructure connected with serving or with inference, so actually running machine learning models, executing machine learning models. Second big challenge is that it's not just data scientists that are required to run machine learning in production. It's a multi-team effort that requires both data scientists and DevOps engineers. And obviously both teams have very different skill sets. And it's very rare to find people who have both, in the kind of unicorn of an ML engineer. So what's very important is as data scientists build machine learning models, that they, when they hand those models over to the DevOps team, they can't, at the moment there's a huge, in many large organizations, a huge time lag before those models actually make their way into production, which could take many months. So this feedback loop causes organizations to reduce the frequency of iteration and ultimately to have a sort of substandard projects. So the infrastructure we created for to solve this problem is based on Kubernetes, which I guess many of you in the room are familiar with. Hands up who's used Kubernetes or using it in your company? Great. So there's like good sort of 20-30%. I'm sure there's a lot more. So we built on top of Kubernetes, and this is not just for serving the deployment platform. It's also for packaging up the models in containers and then deploying those within this infrastructure. So the models can therefore run and scale across any cloud. It can also run on-prem. And Seldon is composed of two kind of core projects. One of them is called Seldon Core, which is open source, and this is focused on model serving and enabling organizations to build out inference pipelines, so serving multiple models. And we're also building a new enterprise product, which focuses more on managing team workflows, so collaboration, things like approvals, and compliance ethics. And this is kind of where this talk is more focused on. So here's an example of an inferencing pipeline. You could deploy a single model, or you could deploy an A/B test, or you could deploy a multi-arm bandit, which is testing the performance of multiple models on the fly. Behind that, but in this case, it's a client-built feature transformer, outlier detection, a Seldon feature. And this inference graph is described in what we call a custom resource in Kubernetes. which is a piece of JSON YAML, which is declarative, so you can kind of check that in to manage it with source control and have better reproducibility. So one of the key components, or Seldon really sits within, because if we focus on deployment, we can sit within other sort of broader end-to-end ML projects or products. One of which we're super excited about is called Housley, which actually originated from Google, from people on the Google Cloud team, and now has about 50 collaborators, including other big companies like Microsoft, Intel, Cisco, Uber, Red Hat, and many more. This brings together, it's an ecosystem that brings together different projects. So you have things like Argo, Ambassador, Jupyter Notebooks. For model serving, there's TensorFlow serving, and Seldon core for sort of any kind of multi-framework scenarios or inference graphs, etc. So we're really proud to be part of that community and really excited where it's headed, and definitely recommend checking it out. But the third sort of cycle, which actually I'll just cite this diagram that's building here, comes from a Gartner paper, which was produced last year around operationalizing AI, so based on feedback from, broadly speaking, to people out in the market, and sort of a kind of common sort of pattern that emerged, that sort of led to this sort of synthesis of the three kind of problem areas, or the challenges. And so the third challenge is around model management and governance. And so that's happening in parallel with the other steps. And obviously missing out on the sort of model management and governance steps massively increases the risk of things like reputational damage and fines from regulators. So this is a challenge which we can solve through addressing a number of different principles. So if we move to the next, here's an example of 8 principles that were put together by the Institute for Ethical AI and Machine Learning. So there's things in here like bias detection, for example, managing transformation, when a model is produced and there's changes that happen through machine learning models replacing certain tasks or jobs, and sort of anomaly detection. And the one we're focusing on here is explainability, but just to reference the founder of this organization, this non-profit called Institute for Ethical AI and Machine Learning, is a guy called Alejandro Salcido, who's very active in kind of the machine learning and ethical AI communities. And we're super excited to actually have him on board as our newest team member at Seldon. He's focusing on solutions engineering, helping us to work directly with our clients to serve machine learning models not just in a scalable way, but in a more sort of ethical, compliant way. He wouldn't be here today, but he's speaking in China at the Startup Conference and various other conferences. So definitely recommend checking out the institute. The URL there is ethical.institute. So more on explainability. So the question here is, can you trust the machine learning model? Trust its output. That's kind of one of the main reasons for explaining it. And this diagram or this image comes from Matt Tegmark's book Life 3.0, which is really a metaphor. So I'll describe what's going on here. The blue stuff is water, and then the green is land, and above it you see mountains. It's really a metaphor for the kind of progress within AI. So within the water you'll see things like chess, which is a sort of very solved problem. Then as you go into the beachheads, you start to see things like self-driving cars and Go. And then further up in the mountains, there are certain activities that we take for granted as being sort of easy for humans, like social interaction. But there are certain things like science, which are extremely tough to solve for humans and obviously for machines. And obviously, when the machines start to figure out science better than us, then it's time to kind of hunker down in the nuclear bunkers and pray for the survival of humanity. Next slide, please. So the problem, go back to the problem, is that as you know, going back to like why machine learning is a black box. When you, in this case, are classifying an image, which is a boot in this case, you're splitting the image into a series of vectors, and then pushing those through a model that you train. And that model is being trained on millions of samples of various different images. Click to the next build, please. And through each phase of training, as you're trying to reduce the loss function, there's various different levels of complex abstraction which have been represented inside the different layers within this neural network. Which makes it incredibly difficult when there's literally millions of these parameters and an increasing number of parameters as we start training more advanced models with great volumes of data. The challenge really is not so much that the model itself is physically opaque. It's that there's just so many parameters inside it that the model is impossible to decipher. The most explainable, and then the other output for things like machine learning classifiers will be generally a probability distribution. So in this case, it's a 90% chance of it being a boot, and it could be a 10% chance of it being a shoe. And so you don't have a full kind of level of confidence into why that's being predicted, and therefore you might need to dig in and explain it in more detail. So you have black box explainers, which is where we focus on mostly with Seldon currently, which if you think about a model literally being sort of behind an API, and you only have access to a predict function, and you're analyzing the inputs and the outputs of that black box. But there are also a number of white box techniques, which you can use when you have access to the model. And you can actually do more interesting things around explaining models when you have actually access to them. So it's not just about black boxes. There are techniques, for example, there's a what if function connected to TensorFlow, which works really well. And you could do more when you have access to the data as well. In this case, you have the two broad types of explanation. You have both a global explanation, which is looking to explain the model as a whole, which generally will be more interesting to the data scientists and developers. Then you have local explanations, which is looking to explain the output of a single prediction, which generally is more relevant for the end users. The diagram you see at the bottom is just showing these two, how the model and the explanation really sit side by side in parallel. The explainer is a little bit like a sidecar that's connecting to the model and kind of interrogating it. So you click to the next slide. Yeah. So what makes a good explanation? They need to be human interpretable, but not overly simplified. So the best, most accurate explanation of a machine learning model is the model itself. But obviously there's a extremely fine degree or high degree of fidelity there. So there's a trade-off because you're making an approximation. When you're making an explanation, it's an approximation of the model, which means there's a trade-off between the fidelity and the interpretability. And each time you create an explanation, it incurs compute costs, and actually, in many cases, will incur a more significant compute cost than just the inference of the model. So it's impractical, costly to explain everything. So you need to figure out which outputs and which predictions you will want to explain. So some of the techniques for doing that include trust scoring. So sort of building a confidence score to figure out how accurate we believe the prediction is based upon the data that's available, and outlier detection. So where you see anomalies, you might want to go in and figure out why those are happening. So there are various different sort of reasons for explaining different use cases, and it's about sort of matching the right kind of question to the right problem. So here's an example of a few different types of explanation questions you might ask. So what is crucial for a prediction to hold? So what are the features that need to be in place for an output to happen? And this is solved somewhat by the anchors algorithm. And then what could you change to flip a prediction, which is related to counterfactuals, which might be used, for example, in when a loan is being declined and the customer wants to request what they need to change about their application in order for it to be a successful application. So click to the next one. So we're an open source business at our core, and we believe very strongly that open research and open source has been a core driver of progress around machine learning, AI generally over the last few years, and TensorFlow has been a great driver of that. So it's just as important that explainable AI is also open, not just for progress, but also for transparency. Because many of these models are being used in cases of kind of compliance and regulatory reporting, excetra, or if an event happened which is becoming, which is quite high stakes, self-driving, very high stakes, self-driving cars or medical diagnosis. People really want to know, why these things are happening. And if they can't do the due diligence on the black box, the model is a black box, and you can't do the due diligence on it in the same way as an open source model. So there are lots of different techniques available, and some of them, when we looked at the kind of landscape for explainable AI, there's some amazing kind of more established projects. But then some of the most exciting things we found were kind of the research, based on research papers that have just emerged, or just had some kind of fairly more brittle code that was developed to just sort of prove a certain technique can happen. And each of these different projects would live in different GitHub repos, have different APIs and ways of actually sort of importing these and using these within your projects. So there was no kind of scikit-learn for explainable AI. And my company, Seldon, and some of the super talented data scientists within it, went about solving this problem with a new open source project called Alibi. And so we released Alibi beginning of May, and it's a separate standalone explainable AI library written in Python. It focuses on both model interpretability, explainable AI, and inspection, so things like trust scores, anomaly detection, etc. We welcome you all to kind of download the project, use it for free within your own businesses, within your own projects, and we're very open to collaboration. So I'll just talk through a couple of the techniques that we see in Alibi that we're excited about. One of them is called anchors, and what that's seeking to do, what that does, is look at the minimal set of features that need to be active in order for a certain output to occur. So in this case, there's two examples. The top one is looking at a data set, or a census data set, and predicting annual income. And the larger sort of blue, the darker blue, green, is marital status, and then the other part is made up by gender. And in this case, it could be really useful for helping to debug and debias a model as well. The other kind of visual representation is showing how the anchor around this beagle is a minimal set of features which will always trigger this classification. So in this case, the other images show different backgrounds behind those anchors, which wouldn't normally happen in the real world. It just serves as an example to show how it works. And we believe that anchors is kind of the successor in a way to Line, which is a very successful, very popular explainable AI library over the last couple of years. It's going to be used for the same use cases. The other one here is contrastive explanation methods, or CEMs. What this seeks to do is find your pertinent negatives and pertinent positives. So this is a classic MNIST example. So you have a 4 on the right, which is your prediction. The middle image is a pertinent negative, which is showing you the sort of minimal set of features which would trigger that to switch from a 4 to a 9 in this case. So that actually, in a way, is a little bit like a counterfactual, which I'll talk about in a sec. And then the next one is the pertinent positive shows you the minimum set of features that need to be activated to trigger this prediction. So if you're just swiping very quickly a 4 on a screen, for example, you don't need to do the whole thing. And so this could be really helpful, generally to explain these use cases. So counterfactuals will answer the question here. So you've got the question here, what prediction should I get if I change feature X and feature Y? So you can rephrase that as saying, what feature should I change to get the prediction I want? This addresses the use case I mentioned earlier around, say, a loan application has been declined, and someone actually wants an explanation of what they need to do to have a successful application. And we've adopted, I suppose, the counterfactual algo within Alibi, but members of our data science team have also extended it and sort of done a little bit of original research, which we'll be publishing as a research paper in the next few weeks. And it's called Counterfactuals Based on Prototypes, and it's inspired by adversarial examples. So I don't know if anyone can see this, but what this shows is a few different sort of differentiated different images, like a puppy and a praying mantis and a key thing. And in the middle is just noise, pretty much all looks the same to us. But can anyone guess what the classification is of the outputs here? So all 3 of these are classified as an ostrich, and this is often be used by kind of hackers or people to manipulate machine learning models. There's ways of producing this noise to mess with the systems, and it will be particularly dangerous in cases like self-driving cars. The noise that's created, in a way, is like counterfactual because it's creating some data which is kind of fooling the algorithm into believing it's something, classifying it as something else. But that noise from the adversarial example is not interpretable. So it's using some of the same techniques, but making this interpretable. So we're really excited to. We actually released it. We haven't released the research paper yet, and we'd love to get some feedback on that. So. Most of you, I'm sure, will have seen the white papers that we've scattered around. So that's something that we put together at Seldon to kind of give a high-level overview on explainable AI. It dives into some other topics as well, based on some surveys that we did. For example, some of the rationale as to why, sort of the reasons why people use explainable AI. So in this case, actually, it turns out that only 10% of explanations are only to serve a regulator. We expect it to be a lot more, but it just shows it's quite early days as far as regulation of the AI. But most of it, like 41%, is for internal stakeholders, and then 39% of customers, so pretty much equal on that. It's currently published for consultation, so it's kind of a draft, and we're open to contribution. So if there's anyone out there that is interested in this space and has something to add, we'd love to chat. So final point, this is more of just like an off-topic announcement, I suppose, or like a kind of a heads up. There's an exciting project emerging called ML-Spec that Seldon is connected to, which is created by a guy called David Aronczyk, who is one of the founders of the Housley project, and actually previously worked at Google on GKE and he's actually now at Microsoft heading up the open source ML strategy. Still collaborates very closely with Google and all the other big companies, and with Seldon, and basically the purpose of this is to try to create a common schema across the entire ML pipeline so that organizations can build platforms and tooling that is more interoperable. And we're really excited about it. We're contributing to it, and we encourage you to take a look and either use it internally or to start engaging with the project. We believe that there could be enough momentum here to have more standards emerging. So we're hiring. It's one of the reasons we host this event, among many other educational reasons. If there's anyone out there that is looking for a job in data science, whether it's hands-on development or other more commercial roles, please come and find me or Lee, who's sitting over there, or Inga, who's the amazing ops manager who helps to bring this event together. We're based in Shoreditch, and we recently raised a big seed round, and we'll be up to about 20 people in the next few months. And I think that's my last slide. So thank you all.